With rational expressions, the important thing you need to remember is that 3 over 2 is a ratio. And that means that it's just writing something with division. And because I can't divide anything by 0, if I have x down here in the denominator of fraction, this means that x cannot be 0. And the more complicated it gets, the more involved these problems become. Now, sometimes people remember this as like talking about an egg. A 0 in the numerator is totally fine because it's not going to roll off the edge of a table. However, a 0 in the denominator would fall, crack, and spilling out the contents inside. So here these problems say excluded values is a heading, and we're going to state the excluded values for each rational expression. So in your textbook you would be rewriting the original problem, and you're not solving for what m would be in these problems. We're not doing the zeros like we did in an earlier chapter. But what we are going to write in our next step is that the denominator, m minus 6, cannot equal 0. So we'll set that equal to 0, which then tells us that, if I add 6 to both sides, m cannot equal 6. Now I keep on saying that they can't be 0, but when we just write these, we write m equals 6. Like I'm saying it does not equal. So technically, these are does not equal problems. But we just keep it simple by writing it that way. Over here, I'll do problem 2. You have to rewrite it again, x squared minus 5 over x squared minus 5x plus 6. And I'm going to give myself a little bit of room here so that I'm not thinking that this is a continuation of the same line of math, because this does not equal that. I'm just pulling apart the numerator. Pulling away the denominator. So now this is a different sort of problem. When I set this equal to 0, I look at this as a factoring problem. So I'm looking for the factors of 6 that add up to negative 5. And that would be x minus 3, that's a terrible 3, times x minus 2. That 3 is still terrible, but a little bit better. And this tells us that x can either be 2 or 3. And I will end up boxing, all of these different excluded values. And just like when you did the factoring chapter, you could go and plug these back into the denominator to make sure that they end up being 0. 2 squared is 4, minus 5 times 2 is 10, plus 6. And then I'd be like 6 and 4 is 10, minus 10 is 0. And then similarly, 3 squared is 9, minus 5 times 3, which is 15, plus 6. These guys give me 15 minus 15 is nothing. And I'm going through that quickly because you can take your own time jumping around in there. Make problems 3 and 4 on your own problems, and I will put the answers up in just a moment. So pause to complete both of these, because I think 3 is easy and 4 is more challenging. I'll put the answer up in a few seconds. 4, 3, 2, 1. Here are the solutions that I got for both of these, and I did rewrite the original problems. I did set the denominators equal to 0. No real factoring or anything complicated was involved in number 3, but because of the coefficient up front here, you were looking for the factors of negative 15 that added up to 14, which was 15 and negative 1. And assuming I didn't make a mistake, that should check out. Let's check out some word problems. Use rational expressions. The ancient Egyptians probably used levers to help them maneuver the giant blocks they used to build the pyramids. Now this is the example of the type of problem where they're just trying to mess with you and then they give you a diagram so you can kind of cheat your way through this. The diagram shows how the devices may have worked using a 10-foot lever. I said lever, then I said lever. Hey, great. The mechanical advantage of a lever, well, do you really have to know all the background to that? No, not really. Is LE over LR. Well, that's clearly a rational expression because it involves division. Where LE is the length of the effort arm and LR is the length of the resistance arm, calculate the mechanical advantage of the lever the Egyptian worker is using. So I'm still thinking about those excluded values, and as a student maybe you're like, well, that's weird, we were just doing that problem. Is this the same type of deal? So we write LE over LR, and those are subscript E's and R's. And then I look at this problem, and I'm like, well, do I know the values for each of these? Well, LE is the length of the effort arm, and since they clearly labeled the effort arm here, I'm going to write is equal to 8. And then LR is the length of the resistance arm. And when I look at the picture, it's just 2. So I'll plug in 2 and I will write 4. So calculate the mechanical advantage of the lever the Egyptian worker is using. We'll go ahead and box this, draw an arrow to this, and write mechanical advantage. So as you probably remembered, but with the simple tools, like when you had pulleys, the more pulleys you have involved, the less work is involved, but then you had to pull this rope way further. So you could lift something really heavy over here as long as you had enough pulleys. And then similarly, you could lift something really heavy as long as you had a long enough lever. The force placed on the rock is the product of the mechanical advantage and the force applied at the end of the lever. If the Egyptian worker can apply a force of 180 pounds, what is the greatest weight he can lift with a lever? So let's just try to take this and turn it into an equation. The force placed on the rock. Force is commonly a capital F. We'll write capital F. And if we want, we can stand this apart by calling it R or something, because it's the force on the rock. So we'll use a subscript R. Is the product of the mechanical advantage and the force applied to the end of the lever. Now, we weren't told what variable to use for mechanical leverage, but in the previous problem, we figured out that it was 4. So I've written 4 for the mechanical advantage, as well as the force applied to the end of the lever. So maybe I'll put F-E for end. And when I see the word product, that tells me I'm going to be multiplying these two guys. If the Egyptian worker can apply a force of 180 pounds, well, then you just have to decide, should I take this number and plug it in here or there? Well, where's he working? Well, is he at the end of the lever, or is he pushing it on the rock? So I'm definitely seeing him put this force over here. So his action is not the same action as what's being pushed up on the rock. Now, I'm on purpose going to do this the wrong way. So let's say I thought that meant, I would put the 180 over here and then do 4 times Fe. Well, if I'd solved that, that would end up being 45. Well, that means he's putting out 180 pounds of work to only lift up 45 pounds. Well, that doesn't really seem reasonable in this problem. And if I head down the wrong path by error checking my work, maybe I can just troubleshoot and figure out, well, I guess FR wasn't what I should plug into, but 180 was. And so that then if I were to do this problem from this angle, I'd be like, okay, cool. He can do 4 times the work by using a lever and lift 720 pounds. And that kind of works with what I was thinking. And then, the whole other deal, too, is, as we did look at the problem, we did think that that would have been 180 going into there. Kelly is going to lift a 535-pound rock using a 7-foot lever. If she places the fulcrum 2 feet from the rock, how much force will she have to use to lift the rock? Well, first of all, it helps to know what a fulcrum is. So over here, I'm going to make a drawing of a fulcrum. And so if you were ever on a teeter-totter, then, somebody would be sitting there while the other person went up. And then the opposite would be true. If that person was going up, that person would be going down. So it's like a back and forth deal. So the fulcrum is that balancing point. So let's go ahead and draw a little arrow to that guy and label it as the fulcrum. Now, I'm picturing a rock on the ground. So maybe I make this look a little bit jaggedy. There's my rock. And now I'm going to draw a lever touching the bottom of that rock. And on purpose, I was kind of planning ahead. I drew this to be a shorter distance here than the distance here. Because as I continue to reread this, she is going to lift a 535-pound. And as I'm going this, I'm trying to transfer the words into a picture to make it easier to understand. She's going to lift a 535-pound rock using a 7-foot lever. If she places the fulcrum 2 feet from the rock, and then as I process what that means, there's the fulcrum being 2 feet from the rock. How much force will she have to use to lift the rock? Well, here's 5 feet. Now, apparently that mechanical advantage deal was important too. And we remember that that was back here where the length of the effort arm, meaning who's putting out the effort, can be divided by the length of the resistance arm, meaning like what we're kind of trying to fight against. And so for this problem, it's just going to be 5/2. And we can keep that as a fraction, or we can write it as a decimal. And then when we jump back to that other equation, we figured out that one force was going to be equal to the mechanical advantage, and I like to write that as a fraction because sometimes that means I can cross things out, times the other force. Now, the force that the person is applying is going to be over here on the right, and the lifting weight is going to be over here on the left. So maybe I'll do F2 and F1 for this one. So I want to know if something is 535 pounds. Now that gets plugged in over there because that is not the force that she's applying. That's the force that she's going to have to overcome. Well, that's going to be 5/2 times F of 1, or in this case maybe K for Kelly. Multiply both sides by 2/5, and I will end up having Kelly's force is equal to 535 times 2/5. And when I look at this, if I wanted to avoid a calculator, I could be like, well, this is going to cross out, and I'm going to end up with 107, and 107 times 2 is 214. Now, I'm kind of doubting myself. Maybe I'm feeling nervous, I don't know. So I'm going to type that into a... Yep, it is. Cool. Okay, so she's going to have to apply 214 pounds of force. And the same as before. What if you had the wrong approach? Well, if she had to apply way more force than 535 pounds, we know that she probably can't do that. That's a lot of heavy lifting. So in this video, we ended up remembering that you can't divide by 0. We're doing some excluded values, but there's no simplifying happening in these ones. And then there's some real-world problems that are all about these levers. So, they all kind of had the same thing going on, so maybe that's going to show up in the textbook. But then in the next video, there's going to be simplifying involved too, with rational expressions. And I think that stuff's really fun. So hopefully you're as jazzed as I am simplifying these. Let's see what goes on. Not simplifying, that's the next video.